Hello, this presentation is on Richard Feynman. It's presented by Jonathan Seagrave for the Math 420 History and Philosophy of Mathematics course at Mayville State University for the fall 2019 semester. I hope you enjoy it. An ordinary genius is someone whom you and I would be just as good as if we were only many times better. But a magician is different. Celebrated as a magician among geniuses, Richard Feynman is regarded as one of the most influential American-born physicists of the 20th century. Known equally well for his humor and his wit, his antics as a classroom prankster, and as an off-hours safecracker, he's entertained a generation of colleagues and students alike. Feynman worked on the development of the atomic bomb during World War II, made fundamental contributions to our knowledge of quantum mechanics, and set the gold standard for the explanation of physics. Feynman came to be known as the Great Explainer for his uncanny ability to simplify complex systems into topics that could be understood by non-magicians. From a young age, Richard Phillips Feynman was intrigued by science and the physical world and has made fundamental contributions to our basic understanding of quantum mechanics. Feynman was born in Queens, New York in 1918. He was the first child of Melville and Lucille Feynman. Richard Feynman's father, Melville Feynman, born in 1890, immigrated to the United States from Minsk, Belarus, when he was 5 years old. Richard's mother, whose maiden name was Lucille Phillips, was born in 1895 in the state of New York. Melville and Lucille married in 1917, and Richard was born a year later. During Richard's childhood, Melville supported his family by working as a clothing store manager. Feynman credited his father for his introduction to science and scientific thinking, recalling at length about how he was influenced by his father to think deeply about the world around him. When Richard was a small child, Melville explained the difference between knowing the name of something and knowing about the thing itself. In a 1973 Nova television program interview, Richard recounted a story where a childhood friend asked him the name of a bird.
Playing in a field, and the kid said to me, "Say, what's that bird? What's the name of it? Do you know the name of that bird?" I says, "I haven't the slightest idea." He said, "Well, it's a brown-throated thrush." He says, "Your father doesn't teach you anything." But my father had already taught me about the names of birds. We walked and he says, "That's a brown-throated thrush." He says, "Know what the name of that bird is? A brown-throated thrush." In German, it's called a Flügelflögel. In Chinese, it's called a Qinglongtong. In Japanese, a Tohatahara, and so on. And when you know all the names in every language of that bird, you know nothing, but absolutely nothing about the bird. And then we would go on and talk about the pecking and the feathers. So I had learned already that names don't constitute knowledge. It's the knowing the name.
When Richard was 9 years old, his mother gave birth to his sister, Joan. Despite their age gap, Richard and Joan were very close. Joan Feynman became a physicist also, and has made significant contributions to science herself. She's known for a lifetime of work, including first explaining how the Earth's auroras interact with the solar winds. She remembers Richard fondly and has given many widely available presentations, sharing her own stories and experiences in the world.
This is my family. My father, mother, big brother, and me. We were a very happy family. We loved each other very much. There was a lot of laughter in our house, and Richard and I didn't fight. So thinking of those years always makes me happy.
Richard grew up and attended high school in Far Rockaway, Queens, New York. He was exceptionally gifted at mathematics and taught himself advanced mathematical topics such as calculus and analytic geometry while still in his teens. Before entering university, Richard had already developed unique personal notations for many mathematical operations like trigonometric functions, differentiation, and integration. As an undergraduate student, Feynman attended the Massachusetts Institute of Technology, where he majored in physics. Feynman did his graduate studies at Princeton University and earned his PhD at the age of 24 in 1942. Immediately after receiving his PhD, he married his childhood sweetheart, Arlene Greenbaum. Richard and Arlene met during high school, and they were inseparable. At the time of their marriage, Arlene was suffering from tuberculosis. She was only expected to live for another few years. In 1943, with World War II in full swing, Feynman was approached by Robert Oppenheimer and recruited to work on the Manhattan Project, a top-secret program that developed the first atomic bomb. He moved to New Mexico with Arlene, and she lived in a sanatorium in Albuquerque, where she'd be treated for her tuberculosis. He lived in Los Alamos with the other scientists and military personnel. Albuquerque and Los Alamos are roughly 100 miles apart, and Richard visited Arlene weekly. In Los Alamos, Feynman gained a reputation for cracking safes, playing bongo drums, and messing with the project's security procedures and protocols. He had a curious way of pointing out his concerns with the project's security.
In fact, most of the complaints was that the security was rather lax in places. There would be big holes in the outside fence that a man could walk through standing up. And I used to enjoy going out through the gate, coming in through the fence hole, and going out through the gate again and in through the fence hole until the poor sergeant at the gate would gradually realize that this guy's come out of the place 4 times without going in once, and he'd kind of arrest me, sort of.
While at Los Alamos, Feynman gained a reputation for being able to get into any lock. The following is an excerpt from a lecture that he gave at the University of California at Santa Barbara in 1975.
Get up and I'd say that we have important secrets and we need better locks. And so one day Teller got up at the meeting I got up at, and he says to me, well, I don't keep my most important secrets in my filing cabinet. I keep them in my desk drawer. Isn't that better? I said, I don't know. I haven't seen your desk drawer. Well, he's sitting near the front of the meeting, and I'm sitting further back. So the meeting continues, and I sneak out of the meeting, and I go down to see his desk drawer, okay? I don't even have to pick the lock on the desk drawer. It turns out if you put your hand in the back underneath, you can pull out a paper like those toilet paper dispensers. You pull out one, it pulls another, pulls another. I emptied the whole damn drawer, took everything out and put it away to one side, and then went up on the higher floor and came back, and the meeting is just ending and everybody's coming out, and I joined the crew like this, you see, walking along with it, and run up to catch up with Teller and says, oh, by the way, let me see your desk drawer, you see. So he says, certainly, he says. So we walk into his office, and he shows me the desk, and I look at it, I said, that looks pretty good to me. That's pretty safe. It looks to me like it's pretty safe. I said, let's see what you have in there. So he says, I'll be very glad to show it to you. He says, putting the key, he opens it, looks, and he says, if you hadn't already seen it yourself. The trouble with playing a trick on a highly intelligent man like Mr. Teller is the time that it takes him to figure out from the moment that he sees that there's something wrong till he understands exactly what happened is too damn small to give you any pleasure.
Feynman's beloved wife, Arlene, died in 1945, and depressed, he immersed himself in the work of the Manhattan Project until the end of the war. After the war, in 1946, Feynman went to Cornell University, where he worked as a physics professor. While at Cornell, he gave the following lecture, where he explains science and the scientific method.
Discussed how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it. It's therefore not unscientific to take a guess, although many people who are not in science think it is. For instance, I had a conversation about flying saucers some years ago with Leighton. Because I'm scientific, I know all about flying saucers. So I said, I don't think there are flying saucers. So my antagonist said, is it impossible? that there are flying saucers. Can you prove that it's impossible? I said, no, I can't prove it's impossible. It's just very unlikely. That, they say, you are very unscientific. If you can't prove it impossible, then how can you say it's likely, that it's unlikely? Well, that's the way, that is scientific. It is scientific only to say what's more likely and less likely, and not to be proving all the time possible and impossible. To define what I mean, I finally said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the result of the known irrational characteristics of terrestrial intelligence rather than the unknown rational efforts of extraterrestrial intelligence.
In a different lecture, also recorded at Cornell University, Feynman explained the difference between mathematicians and physicists.
Now I would like to make a number of remarks on the relation of mathematics and physics, which are a little more general. The first is that the mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now, I explain that. If you state the axioms, you say, such and such is so, and such is so, and such is so, what then? Then the logic can be carried out without knowing what the such and such words mean. That is, if the statements about the axioms are true, are carefully formulated and complete enough, it is not necessary for the man who's doing the reasoning to have any knowledge of the meaning of these words. And he'll be able to deduce in the same language new conclusions. If I use the word triangle in one of the axioms, there'd be some statement about triangles in the conclusion, whereas the man who's doing the reasoning might not know what the triangle is. But then I can read his thing back and say, oh, a triangle, that's just a three-sided what have you, that's a so-and-so. And so I know this new fact. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. It's necessary to, at the end, to translate what you figured out into English, into the world, into the blocks of copper and glass that you're going to do the experiments with to find out whether the consequences are true. And this is a problem which is not a problem of mathematics at all.
He left Cornell in the early 1950s, spent some time lecturing and teaching physics in Brazil, and went to work as a professor at the California Institute of Technology. In the early 1960s, Feynman was convinced to give a series of lectures for the introduction of physics to new undergraduate students. He agreed to deliver the course on the condition that he would only give it once. In 1961, he began a 2-year series of lectures that would become the Feynman Lectures on Physics. These lectures have become a hallmark of physics education. Feynman's contributions to physics are many, and there can be much debate as to which of these contributions are the most significant. He was among the first to apply the principle of least action to quantum mechanics by introducing what has come to be known as the Feynman path integral. He contributed significantly to the foundations of quantum electrodynamics, a theory of how light and matter interact with considerations for both quantum mechanics and relativity. This work would, almost 20 years later, earn him a Nobel Prize in 1965. In January 1986, the Space Shuttle Challenger exploded shortly after liftoff, shocking the nation. Feynman was invited to be a member of a commission assembled to investigate the cause of the disaster. He famously demonstrated the lack of resilience in the material used to seal seams in the rocket boosters by holding a piece of the O-ring plastic in ice water and showing that it did not remain elastic while cold.
Commission member Richard Feynman, after examining the O-ring, had a surprise.
Oh, I took the stuff that I got out of your seal and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it maintains, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, There's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
Richard was diagnosed with liposarcoma, a cancer of the fatty tissue, in 1978, and by the late 1980s, he had several surgeries to have tumors removed. He died in 1988 in California at the age of 69.
You could see him struggling, and what his last words were, "This dying is boring. I wouldn't want to do it again."